Hello everyone, my name is Charity. I am a student volunteer at ABC Impact. Today we will be continuing on learning organic chemistry. This is part three of our organic chemistry form 3 hydrocarbons, and we will only be learning alkenes, and we won't cover all of alkenes because there's a lot to learn about alkenes this time. But we will do the rest of the alkenes in another video, and we'll do some of the alkenes in this video. Okay. So let's get started. So this is what you need to know for alkenes. So you will need to know the general formula, the occurrence and nomenclature up to 6 carbons, but it's recommended you know more than that. Similar, like most of it, if you know up to 10 carbons, very similar to alkanes, you can very easily remember it. Then you also want to know isomerism. So things like butene and pentene isomerism. Then you will also want to know chemical properties and your combustion reactions, your addition reactions. Addition reactions you haven't done with alkanes, so this will be very new. A lot of the addition reactions with alkanes are possible because of their double bond. Additionally, you want to know their physical properties, and these trends are quite important for you. Then you have the test for unsaturated. This is the test whether they have the alkene or the chemical is unsaturated or not. And then you'll have school preparation of ethane. And also, you want to know what ethanes and alkenes are used for. Let's go to the first thing. So here we have our carbon molecule. So how do I know this is a carbon molecule? Please tell the person next to you why I know this is a carbon molecule. Excellent. So unpausing the video now, we understand that this is a carbon molecule because we can see at the center inside the nucleus, it has 6 carbons, or 6 protons. And we know that carbons have 6 protons. We can also see that this is a carbon molecule and it's a neutral one because we see that there are 6 protons in the center and then there are 6 electrons on the outside. So we can see here is our diagram of our molecule. We have our blue little dots as electrons, and then we have the red as protons. Awesome. So now that we know this is a carbon molecule, I've drawn what the carbon molecule actually looks like. And this is slightly different from the previous slide because in here, I've specified that we actually have valence electrons and non-valence electrons. So if you know, hydrogen only needs to have 2 valence electrons because hydrogen needs only 2 electrons in its outer shell, the valence shell, to be happy. However, all the other atoms in the second row of the periodic table want 8 electrons in their valence electron shell. And so this is the same for carbon. Carbon follows the octet rule. So it wants 8 electrons in its outer shell. Because the inside shell is 2, we don't need more electrons for that. So even though carbon has 6 electrons, it wants 4 more to fulfill the octet because the 2 already fill the smaller shell. So if we look at carbon right now, we can see that it perfectly has enough electrons to form 4 bonds. And this is why carbon is so unique and so important for organic chemistry, because it has 4 bonds. It can form it's very stable because it has 1 bond on this side, the other bond on this side, and then a bond on the left and the bond on the right. And we see here's what a carbon-carbon single bond looks like. So this is a very classic case of a carbon-carbon single bond. And then we can see, okay, so since carbon wants to be happy with 8 electrons, it will form a covalent bond, and that is called sharing of electrons with these other hydrogens. This is covalent bonding. So then, let's say we take away 2 of the hydrogens. So we take these 2 hydrogens and we take them away. Okay, so now we don't have a hydrogen on this side. However, carbon wants to be happy. Carbon wants 8 electrons in its outer shell. And let's count the number of electrons in this outer shell. So let's count the number of electrons. 1, 2, 3, 4, 5, 6, 7. This carbon has 7 electrons. Let's count for this one. 1, 2, 3, 4, 5, 6, 7. All right, the question is, why do these carbons only have 7 electrons and not 9? Because we see that this carbon actually has 3 electrons that it's sharing. So technically, then on its own, it only has 1, 2, 3, 4 electrons. So this is because we are missing 2 electrons. The 2 electrons are not in the valence shell, so they are not important for bonding. So when we draw bonds, we will omit and not draw the 2 electrons inside that are not part of the valence shell. So this will make it easier. So we will pretend the 2 electrons exist, but we will just not see them. All right, so these carbons want to be happy with their 8 electrons, right? So what they will tend to do is they will start to bond, right? There's a potential and a possibility that these 2 carbons can also share these 2 electrons. So we move this to here, and then now we have the carbons are happy. They each have 8 electrons. So let's take a look at alkenes and their information. So first we have a general formula where if you have N carbons, you will have 2N hydrogens, assuming this is a standard alkene and they do not have any extra branches and they do not have any extra substituents either. As well, we can know their occurrence. So their occurrence is that these alkenes are often obtained from the cracking of alkanes. We will learn about that later on today. The nomenclature, it's best if you know it up to 10 carbons because this is very similar to alkanes. If you understand alkanes, you will also be very quickly able to understand alkenes because a lot of them are the same. As well, we want to know that our alkenes are also, like alkanes, non-polar. Our alkene and alkane non-polar. They are also colorless, and they can be gases, solids, and liquids, and they are usually not poisonous. There are exceptions, but for the most part, they are not poisonous. So, for your next task, please draw 8 of the alkene homologous series. Do you guys remember what the alkane homologous series is? So, please apply that to the alkenes. Please draw the 8th alkene homologous series. So from the first alkene homologous series to the 8th. And please name them as well. Pause the video now and try it yourself. Unpausing the video now, we will see that this is our 8th homologous series. We have ethene, propene, butene, pentane, hexene, heptene, and octene. So for those of you who have done alkanes, you will see very quickly that all these prefixes are the exact same as the alkanes, and then the suffixes are unique to alkenes because they have the E and E. And you can see that in the structural formula, there's a double bond. So some of you might look at your friends' drawings and notice that you guys have different placements of the double bonds, and that is okay as long as we are talking about the homologous series and you have matched the correct molecular formula, which is CnH2n. That is the correct answer for this exercise. However, you will later learn that sometimes we will have to specify where the double bond is placed. Let's talk about saturation. So these are both fat molecules. What is the difference between these 2 molecules? Please pause the video now and answer it. Unpausing the video right now, you guys can all see that the difference between these 2 fat molecules is that this one has a double bond and this one does not. So you can notice that the double bond is actually making the molecule look crooked. And this is a very interesting phenomenon. This is also a very important part because this one crooked double bond changes the fat molecules. We can see that the top one is saturated and the bottom one is unsaturated. So the top one has all of its carbons joined to as many hydrogens as it can. And the bottom one, because of the double bond, because the carbons are sharing their electrons, they cannot add another hydrogen here because the electrons are already being shared by each other, so they cannot add another covalent bond to a hydrogen. We will see why this unsaturated molecule is so important, because you notice that this crookedness of the molecule actually never changes. And we will see right now
Atoms which are linked by a single sigma bond can rotate about the bond axis. That is why alkanes are characterized by free rotation around the carbon-carbon bond. The situation is different in alkenes. The nature of the double bond requires the p orbitals forming the pi bond to be parallel to each other. Because of this, rotation around the double carbon-carbon bond is restricted in alkenes. This restricted rotation around the double bond in alkenes results in the phenomenon of geometrical atoms which are...
Excellent. So, these are both fat molecules. Again, the difference between them is because one of them has a saturated carbon backbone, and the other has an unsaturated carbon backbone, as you can see here. So some of you guys may be seeing another double bond, and you can see this double bond right here. This is a carbon and oxygen double bond. This carbon and oxygen double bond, combined with the fact that it is also connected to an OH group, an alcohol group, makes this a very, very special functional group. So this would not be considered an alkene. So let's say at the top you see this saturated molecule. This is not an alkene because the carbon is attached to a double bond with an oxygen. At the bottom, this is an alkene because you have these two molecules right here, these two atoms, they are attached to a carbon-carbon double bond. So this at the side is a different functional group. It is not an alkene functional group. So you notice that we've been talking about the alkene functional group and why it's so special. So the carbon-carbon double bond in alkene is a reacting site. It is very important, and it is often the place where a lot of reactions will happen. So what does it mean that it's the reaction? It means that these two bonds will likely change in a chemical reaction. And that is why it's called the reacting site, because they're the most reactive. So compared to changing this carbon-hydrogen bond, reactions will like to change and switch up this carbon-carbon bond. And you will see that we have a list of our functional groups here. And we will see that alkenes are also on the functional group table because they are so important. They change the functional group points is that they change the property of the whole molecule, and they allow this molecule to have more different types of behavior and different types of properties. So most of the reactions of alkenes take place at this carbon-carbon bond. And this is why alkenes are more reactive than alkanes, because they have that double bond. So alkenes will likely have more reactions, and you'll see this later on, because later on we will look at the types of reactions that alkenes can have, and they have a much longer list than the alkanes. Why? So why is the double bond more reactive than the single bond? So here we have two molecules. One is ethene and one is ethane. We have only drawn the valence electrons for ease of viewing. So you can see here that this carbon is attached to another carbon in a double bond, whereas this carbon is attached to this carbon to a single bond. And we can see immediately that one of them is more stable because the double bond has more electrons than a single bond. And why are electrons important for reactions? Well, let's take a look at the protons. The protons are inside the carbon nucleus. The protons cannot move, right? So the protons can only move with the carbon molecules. However, electrons are much smaller and outside at the valence shell. So at the valence shell level, the electrons will switch around and move much more freely. And so when we have a lot of electrons in one area, this causes more electrons to be in that area, which means that there's a lot of negative charge in this area. So if another molecule comes around, it will likely attract these electrons over these electrons because there is a lot more negative charge, and negative charges repel negative charges. Remember, this is like charges repel and opposite charges attract. So that means that these unsaturated hydrocarbons easily react to be hydrosaturated. We will then talk about isomers. So we notice that this double bond can be in different positions on our molecule. So for example, this is butene. These two at the top are butene, and this one is also butene. However, we would not name this in IUPAC as butene because the longest continuous carbon chain is only 3. So we name this propane. However, you can see that changing up the position of this carbon bond from position 1 to position 2 will change the molecule as a whole because the double bond cannot jump to a different carbon. So these two are very different molecules. I have a question right now. What if instead of this bond being here, we wrote it out and we gave this one a double bond? What would that be? Pause the video right now and try it out. Unpausing the video right now, we can see that now this molecule, now that it doesn't have a double bond here, this molecule is the exact same molecule as this molecule at the top. The reason because we always want to start counting the carbon chain from the important functional group, right? So when we number off 1, 2, 3, 4, at this point, because the functional group was on this side, we will number 1, 2, 3, and then 4. And this causes then this carbon chain to be the exact same as the one on the top. So that's why if we had a carbon chain on the last one, it would be the same as the first. On the other hand, this one is different because there's a branch. So please name these molecules in IUPAC naming. Pause the video now and try it out. Unpausing the video now, we will go over the answers. So we have but1ene and but2ene. The 1 and 2 come from the position of the alkene double bond. At the end, we have another molecule, 2-methylprop-1ene. And so 2-methyl is because we have a branch on the second carbon. Finally, something that is good for you to know, but is not important on the test, is that there is a third type of isomer. So you can see that but2ene and but2ene down here both have a carbon double bond on the middle 2 carbons. However, the placement of the carbon chain is different. One of them goes from here, from up to down to sideways to up again. But the other one goes from down to up to sideways to up, which is different than the top one. And you can see this very clearly in the picture right here when we have drawn out the line bonds drawing, which the line bond drawing will ignore the hydrogens. And this is again the reason here.
At each other. Because of this, rotation around the double carbon-carbon bond is restricted in alkenes. This restricted rotation around the double bond rotation.
So you can see right here that because the rotation is restricted, this Y molecule does not end up on the same side as this molecule. In fact, they are always going to be diagonal from each other. So we can see right here, there are 2 types of isomerism for alkenes. The one that is important for you to know is positional isomerism. That is where you have the same number of carbons and the same formula. If you counted out all the carbons and all the hydrogens, you would have the exact same amount. However, you can see here that it moves along the carbon backbone, this double bond, and that is what gives it positional isomerism. On the other hand, you have the thing that we talked about in the video. So we have the geometric isomerism, which has the carbon double bond at the same location. However, the different branches or the ways the rest of the carbon chain connects these 2 carbons, the carbon-carbon double bond, are on different sides. So you have 2 of them on the same side, and then you have 2 on the opposite side. These little white balls are hydrogen, and so you can see very clearly why these hydrogen are mostly ignored in the line bond drawing. Finally, we have two cases of isomerism here. Please name both molecules on the right. Pause the video now and try it out. Unpausing the video now, we will see that this one is hex 3 ene. The top one is hex 3 ene because either way, no matter which side you number off, you will be 1, 2, 3, or 1, 2, 3. So the carbon-carbon double bond sits nicely in the middle, and it's always going to be starting with 3. On the other side, this one is hex 1 ene. Hex 1 ene. This is because the double bond begins on the first carbon. And we numbered this the first carbon because it is the lowest numbering in the IUPAC naming system. Finally, I want to go over an even harder example. Please look at this example with me. You can try it out yourself later on in the practice. However, I want to bring your attention to trying to make patterns in the molecular formula. So here you can see we do not draw out the structure of it, but we can still see there are patterns. So you can see very clearly that this carbon plus hydrogen are kind of grouped together. And then there's this carbon, which has no hydrogen attached to it, but it is attached to another methyl group. Because we know that this is a methyl group. It's a methyl branch. This is CH3, right? CH4 is methane. CH3 is the perfect number of hydrogens and carbons for a single branching methyl. And then you have another C. And then we have a CH3, another C, and a CH3, and then a CH3. So these are a lot of methyl. So let's try to draw this out. When we draw this first carbon, right, we know that it has attached to 2 hydrogens. We want to see, okay, so then it's attached to another carbon, right? And this carbon is attached to a methyl group, right? So we don't need to draw all the bonds for the methyl group. We know what a methyl group looks like. And we know that this methyl group is only attached to this carbon because the reason is that this carbon is filled up, it's saturated with all the other hydrogens, so it can only have one connection with another carbon. On the other hand, this one, it also has another C. And then it also has another methyl group. And then we have another C. And then we have a methyl group. And then we have finally a CH3. So here we realize that we are also missing hydrogen. And understanding this, seeing the patterns of this, will be able to help you name your carbon atom. And we notice here that because we are missing hydrogens, they must be double bonds. Because if we had hydrogens, they would be single bonds. But because we are missing hydrogens, we know that they would have to be a double bond. So here we can see that we have 2 double bonds, one at position 2 and one at position 3. And it doesn't matter which side you start counting from, you will always be counting from. You will also be having position 2 and position 3. For the students who realize and corrected my mistake, congratulations. Putting the carbons next to each other, putting the 2 double bonds next to each other would actually result in a carbon having 5 bonds instead of 4. So that one is not a carbon we want to have, right? Carbons can only have 8 electrons at max and 4 bonds at max on its valence shell. And so we have our final answer, which is 2,3,4 trimethylpent 1,3-ene. Next, we will talk about the physical properties. We have our line of alkenes from methane down to dexane. First, let's talk about alkanes. We know that all alkenes and all alkanes are not supposed to be soluble in water, but they will be very soluble in other organic solvents. When we review our alkane physical property chart, we notice that because we are growing in the carbon chain as we go from the lowest homologous group to the higher homologous groups, we increase in our van der Waals and intermolecular forces. So this is the only reason for why we made these trends in alkanes. And so when we look at our alkene, for example, we have ethene and dethene, then we can also see that the same trend will happen. The van der Waals and intermolecular forces will increase as the carbon chain increases, because one ethene connecting to another will have maybe like this many van der Waals going on. But however, decene, no matter where it is, it will have a lot of van der Waals forces going on. And so that will make it more stickier. And these decene molecules will stick closer to each other, which will affect the trends in the physical properties. So everyone, please take a look at this chart and please try it out yourself. Unpausing the video right now, we can see that this is the alkene physical property chart. It is the exact same as the alkane physical property chart. And this is again because we are looking at the van der Waals forces increasing. So this is because we are also comparing within alkenes. So we notice that we are comparing, let's say, butane versus heptane or decene versus ethene. So within these molecules, we are comparing a double bonded molecule with another double bonded molecule, and that will make these two very similar to each other. And all the difference between these two, they both have a double bond, decene and ethene. However, the difference between these two is that they have different carbon molecules. And between the alkanes, we have butane versus heptane. And the difference between them is that they all have single bonds, but the number of carbons on the carbon chain is different. So we can see back here that this is our difference between alkenes versus alkanes. So alkenes will have this double bond, and alkanes will have these single bonds. So because we have these differences, we know that the number of carbons are all the same between alkenes and alkanes. And so because we know that the number of the number of carbons on the carbon backbone is the same, we can be directly comparing them for the effect of the double bond with the single bond. And because we know that double bonds are more reactive than single bonds, we will know that alkenes are more reactive than alkanes, and therefore they are more likely to be part of chemical reactions and more likely to actually lose that single bond. So this is sort of what you will be asked to compare when you're talking about properties or reactivities, right? So you will either be asked to compare the different number of carbons on the carbon chain. So within alkanes, you will be comparing an alkane versus an alkane, or an alkene versus an alkene. Or you will be asked to compare different functional groups. For example, butane versus butene, or nonene versus nonane. However, when you have something like butene versus propane, you notice that butene and propane both have different number of carbons and different number of functional groups. Then this is a lot more difficult. So you cannot compare this with normal trends. You will have to either be taught this specifically, or this is like an exception. That's something you want to know, right? So this is not something we can compare using normal trends. For alkenes, we want to talk about the occurrence. So earlier I told you guys that alkenes occur when cracking happens. So what is the definition of cracking? Cracking is breaking down long alkanes to smaller and short alkanes and alkene and also hydrogen gas. So the example we have here is heptane. So we have a heptane and we actually turn it into pentane and ethene. And you notice here that we don't actually produce hydrogen gas. So sometimes hydrogen gas is not produced. So this is kind of the general formula you want to know for cracking. So you have an alkane and you have it at a very high temperature, and this is very important. It must be at a very high temperature. And then when cracking the molecule, you will get a smaller alkene and a smaller alkane, and sometimes you'll get hydrogen gas as well. Now we will talk about our school lab preparation of alkenes. So there are two ways actually to prepare alkenes in a school lab, and one of the ways is through concentrated hydrogen sulfide. So it must be concentrated. Please note that it must be concentrated sulfuric acid. And then you also can prepare from aluminum 3 oxide, so Al2O3. And so these are two different methods. So we will go over using concentrated sulfuric acid first. So this is how you prepare ethene from ethanol using concentrated sulfuric acid. Notice that ethanol has a functional group, which is an OL, while ethene has a functional group that is ENE. And they both have the same number of carbons. So what is going to happen first is that the concentrated sulfuric acid will be added to ethanol at a very high temperature. When it heats up, it will go into this tube and it will go down into this big glassware. This glassware also contains sodium or potassium hydroxide solution. So because when concentrated sulfuric acid is added to ethanol, it doesn't just produce ethanes, it produces some other molecules as well. So the sodium and potassium hydroxide will remove the other molecules from the gases here, and it will leave only ethene to travel through the end, and then we will get pure ethene gas. So step one, we add 100 sulfuric acid from ethanol to form ethene. You notice that we call this step dehydration or removing water. Let's go back and looking at ethylene. So ethene adding water actually becomes ethanol. So this is a very common reaction. This is a reaction you'll be required to know later on because this is part of the hydration reactions where you add water. The reason why it is called a hydration reaction is because you're adding water. Whereas if you went the opposite way and you went from ethanol to ethene, you actually remove water from ethanol, which technically it looks very strange because it seems like you're producing water, but it means that you're removing water from ethanol, right? And so in this case, when you remove water from ethanol, you form ethane. In here, in our diagram, we notice that there are two other types of impurities that are produced. You have carbon oxide and sulfur oxide gases. And so this can be removed, these impurities can be removed, like I said, with either sodium hydroxide or potassium hydroxide. So now that you understand how to use concentrated sulfuric acid to produce alkenes, these are the steps to prepare alkene in the school lab, like the equation below. I'm pausing the video right now. Here's the answer. First, we want to add concentrated sulfuric acid. Please ensure that you remember it is concentrated sulfuric acid. It must be concentrated. Otherwise, it will not be strong enough to produce the reaction. It is added to ethanol and then heated to 180 degrees Celsius to produce ethene and then purity. And then purities are carbon oxide and sulfur oxide gas. The gas is then added to a closed container with sodium or potassium hydroxide solution. This solution will remove impurities. And of course, at the end, we want the ethane to gas to be isolated away from the sodium and potassium hydroxide. So we can then, what we do is we place the tube into another container with water, and the ethane gas will float to the top. So this is our tube. So we want to take the ethane into this tube and through the water. And so once the water is in this isolated container, the ethane will just float to the top because the ethane is a gas and water is a liquid, and ethane is less dense than water. So then we have another question. Please read the question and answer the question below. I'm pausing the video right now. The chemical reaction for this question has two answers. So you want to write both of them for full marks. And you notice that butane-1-ol and butane-2-ol are very different because they are positional isomers. They cannot be the same molecule. So what they will do is butane-1-ol will be dehydrated at the first position. So it'll form a double bond at the first position. However, butane 2 will form a double bond at the second position. And so you can see right here that this is reflected where we write our OH bond, whether it's on the first carbon or the second carbon, right? So in here, we notice that we are numbering 1, 2, 3, 4. And on here, we're numbering 1, 2, 3, 4. So we actually change the numbering, but being able to spot these patterns, this is an N group, this is an N group. And these are inside groups because this carbon will need 2 bonds, and this carbon will need 2 bonds. This carbon will need 2 bonds, and this carbon will need 2 bonds. Is very important for determining sort of where you're numbering and where you're understanding the bonds come from. So of course you want to add concentrated sulfuric acid, and then you'll produce your ethene or your butene molecule at the very end. So the other way is to use aluminum oxide. So here you'll see that we have some glass wool soaked in ethanol, and then we are going to heat it up. And then we have some aluminum oxide in this. So aluminum oxide is sort of like a metal. And what we're going to do is we heat it up, and then the gas is going to come, the ethene gas is going to come through this tube, and then get collected in this isolated container. So what is actually happening with our ethanol and inside our container right here, and our glass wool, is actually, it is reacting with aluminum oxide as a catalyst. This is why there's no impurities, because aluminum oxide is not actually in the reaction. All that is actually reacting is ethanol goes to ethene right away. There's no changing or adding of the aluminum. There's no changing or adding of the aluminum oxide. What the hot aluminum oxide is, it acts as a catalyst, so it's actually not used in the reaction. However, it still is able to allow this dehydration reaction to happen. So you can see here that we lose this OH bond. We lose the OH molecule into water. So here we can see that we've lost this hydrogen and this OH to form a double bond instead. So here is the question. Please pause the video right now and try it out. Unpausing the video right now, we can see again, because these are positional isomers, you cannot make them into the same molecule. So if you have butane 1-ol, you will end up producing but1-ene. And if you have butane 2-ol, you will end up producing but2-ene. So some cautious things that you will need to know, and this is something that is very important. So when you are using concentrated sulfuric acid, so our concentrated sulfuric acid is highly corrosive on skin contact. So because it is an acid and it is a very strong acid, we don't want to be playing around with it, so we have to be very careful when using it. Additionally, there's this thing called bumping. So you can see that bumping will happen in a flask. And so we can see back here, when we are using concentrated sulfuric acid, we are actually heating up ethanol in liquid form. However, when we are doing it with our aluminum oxide catalyst, what we have is a much more drier way of performing the reaction, because it's glass wool soaked in ethanol rather than liquid ethanol being heated up and becoming gas. So we will show this video right now.
Okay, class, this is what we refer to as bumping. A sudden, abrupt, large boil bubbles that comes out of our reaction. So this is a bumping event. Okay, to prevent this from happening, we can make use of a magnetic stirrer to steer the liquid inside to prevent this, or we can make use of boiling chips or boiling glass to deliver small bubbles instead of one large evaporation bubbles like this one. So again, this is bumping, which
So you can see that what bumping does, it actually can be quite dangerous. So bumping can sometimes explode the molecule, and sometimes it can explode the flask, or sometimes it can also be move the flask around and just not boil very evenly, which sometimes causes the reaction to not work as well. And so what you want to do is just put some broken porcelain, some sand, or a boiling chip, or like they mentioned in the video, a magnetic stirrer. Additionally, the temperature should be maintained at above 160 degrees Celsius. At lower temperatures, another compound, ether, is predominantly formed instead of ethylene gas. So this is especially important because when you're doing the reaction with sulfuric acid, it's because over here you are actually physically heating up the ethanol. It is also important to do with the aluminum, but it is slightly easier because this is a catalyst. Whereas for this reaction, you have to be monitoring a lot more. Caution, ethanol is highly flammable because it is an alcohol. We know that it is very highly flammable. And additionally, common school thermometers have a maximum calibration of 110 degrees Celsius and cannot be used. It will break and crack, and that can be very dangerous because it will hurt your skin, and this is not something that is good to do. Then, let's go back to our cracking example. So this is the cracking example question we talked about earlier in the class. Please write the chemical equations for both questions. Unpausing the video now, we will see that the chemical equation for when propane undergoes cracking, it produces methane over here, which is in gas form. It also produces ethane, which we also know is in gas form because ethene, propane, and butene are all in gas form. And it also produces hydrogen gas, ensuring that the chemical equation is balanced. We see that it is, and then we can continue on. So the next question is octane undergoes cracking to form hydrogen gas, butane, and butane gases. So in this case, again, the chemical equation is all balanced. So all we have to do is draw out or write out the chemical formulas, and we will have completed our questions. Now we will finally go on to the last step of alkene reactions. So alkene reactions has a lot, and you notice that we actually have a lot more than previously. So for alkanes, all we had to do, we added chlorine and bromine reactions. But however, for alkenes, because they are so reactive, they will have all these reactions now that you'll have to know. And so because there are so many reactions, we will be going them over in the next video. Thank you for listening.